this meeting, I want to talk about something about sparse coding. And since this topic actually, there have been so many researchers have investigated this topic, so there are so many contents in this meeting. I want to give a basic story of sparse coding. So in the beginning, my content is based on the following two documents. First one is the tutorial in SCCB conference in 2009. Another one is the book named Sparse and Redundant Representation, and by Michael Gilad. And before we enter into this topic, we just want to know the motivation and some basic concept of the sparse. That means why we want to use sparse in the signal processing. And so, for example, if we have vector and different with the general vector, if we just have a small number of elements on non-zero, and we call it a sparse vector. It's different from general vector. And specifically, for example, if we just has 3 elements on non-zero, we call the sparsity is 3. So why we want to use the sparse vector instead of the general vector? It is because there are some obvious advantages over the general vector. Since, for example, if we calculate this vector with other vector or matrix, then we can just calculate, for example, these 3 multiplication. Or in signal processing, if we want to store this matrix or vector, or we want to transmit, and we different with the general vector, we can just transmit operation and the value of this 3 non-zero vector. So it does have some obvious advantages over the general vector. And another important basic concept is norm. For example, in the 2-dimensional Euclidean, we can denote the 2-dimensional Euclidean distance as 2 norm, and its definition actually. It's just like this, and we have familiar with the 2 norm as Euclidean distance, and 1 norm is just we calculate the absolute value of this, and the 0 norm we can easily consider 0 norm as the number of elements here. And next, I want to propose the problem about this in signal processing. And suppose we have original signal called y, and the size is m0, 1 column. And if we want to reconstruct using a matrix and a vector, that in here we call some dictionary and coefficients. And we want to denote original y by some dictionary and the corresponding coefficients like this. So A size would be n rows and n column, and x is just n column, one row, n rows, 1 column. And so in sparse representation, generally we will consider so-called m is much less than n, and we call it over-complete condition. And since m is much less than n in linear algebra, we know this equation is so-called underdetermined equation. And as we know, so we may have an infinite solution here. So the question is, how can we find an optimal solution? Or is there any unique solution here? And there are some general methods to solve this infinite solution. And one common use is the so-called regularization, or we can just we give some additional criteria for some penalty function. For example, one often used is we give for example, we want to get this solution, and at the same time we want to minimize this L2 norm. And so how to solve this kind of equation? So we can use Lagrange multiplier method. That means we make a new function, Lx is equals plus, and also we need a Lagrange multiplier here. You know, in this equation, so it has infinite solution, but when we transfer to this function, so we can use Lagrange multiplier, and we make the derivative of this x. You know, when the derivative equals to 0, we find the optimal solution. So it's equal and so if it's 0, we find the unique solution here. And this is the unique solution we want. Since y equals ax, that means y equals we can get the lambda value. It's just like this, and put the value of lambda into here. So we get x equals lambda A transpose A transpose. So this dictionary and original single it is known variable here. So in this L2, we give the regularization of L2 norm, so we can get a unique solution. That means L2 norm leads to a unique solution in our problem. And the book also introduced that since L2 norm is a convex function for any other convex function here, we can get the unique solution. But I didn't read about how to prove this one, so maybe we can discuss later. That means for any convex function, we can get a unique solution. So at this point, we get a unique solution. However, just think about our original question. That means we want to get the solution. At the same time, we want to get the sparse solution. The sparse definition of sparse is kind of similar with the L2 norm. That means some norm is small, distance is small. However, the real definition of sparse is the number of non-zero elements is as small as possible. Even though so we can get this value is so small, but we cannot make sure the number of non-zero elements is small. So it's totally different with L0 norm. And since L0 norm is not convex, so we don't know whether we can get a unique solution here. And actually, the book also proved that under some conditions, for this L0 norm regularization, we can get unique solution. And as we know, for L0 norm regularization, this is a problem of NP hard. Actually, I didn't understand. I think maybe my understanding is not correct exactly. So what NP hard is, we just want to show, for example, in our example, if we want if we give L0 norm and with sparsity, p-sparsity, if we don't have some solution to solve some method to solve this equation, so we have to try all kind of possible combination of the bases. And for example, if we the number of these bases is 2000, if the sparsity is 10, that means how many times or the time complexity. So we can describe it like that. So we will try this calculation times this value, and it is this number. So if the computer will calculate every calculation, it costs 1 nanosecond. So each this years to try all the kind of combination of 10 sparsity. And similarly, if in 2000 vectors we find 10, 20, 30, or 30, this number is also huge. So my understanding is that in practical computation time, so it is we cannot solve this kind of equation. So this is my understanding of NP hard, but I don't know whether it's correct or something. And so next I want to introduce, since this problem has been investigated for several years and several researchers, so there are some common used methods. In this meeting I want to introduce basic methods how to solve the L0 norm. And the method is based on so-called greedy algorithm. That means in every iteration, in every current step, we want to get the optimal solution in current step. So our question is actually we have original signal, we have because in here we will just consider the dictionary is known. So the only unknown is this coefficient x, and so this is our problem, and so we can just introduce this method based on greedy algorithm. We can just first one I will introduce the matching pursuit, and before the mathematical introduction of this one, I want to just show some common use three-dimensional. We will find so step by step consistent method. This dictionary we have in one. Since in this dictionary we don't need every basis is orthogonal, so generally it will be not orthogonal in one. And if original sequence is like this one. So at the first step we will find so which basis has a maximum correlation with the original signal. So maybe it's here. And the projection is the largest among all of the bases. And so in the first step, we find the selected basis is E2, and we can find the corresponding X2 just this value. And after the first step, or in a single line, we have this so-called residue R. And first step, we selected one basis and coefficients. And for the next step, we have R1, and we will do this step one by one, and until we find this value. That means selected basis, number of selected bases is smaller than the case margin in this case. And so I want to study in mathematical. We have a residue, and so in the beginning the residue is original signal, and we have these coefficients. Similarly, from the beginning is 0. And since we have known this dictionary, but we don't know which basis we are selected, so we call it support, and support will be 0. And after the initialization, we will enter into the iteration.
What's S?
S is, for example, we have one solid basis in A, right? So the support, S means support. That means in this one solid items or basis. So which one we will select it? So in the beginning, nothing will be selected.
Okay.
You mean of the 0 is empty, yes?
Empty. Yes. So we enter into this iteration, and we will calculate which item or which basis has the maximum correlation with original signal. And for this iteration, for step K, so that means first of all we will find which basis we will select. That means the maximum correlation or maximum projection we can use in concept of inner product. We will try all the bases in V and find maximum in J and R. And we will try all the bases, find which one is correlated with residue. And when we find the EJ, we will put the EJ into the support. So we will update support S key. And first S key equals S key. If we find the maximum is 0, select it. After this calculation, find selected is 0. So we will put the selected basis into our support, and we will update the coefficients xk, and the xk also equals first one. We give the last steps coefficients to the current coefficients, and the will put the selective coefficients into last step's coefficients. And last one is update residue. And residue equals over actually it's J0 equals to and update this residue. So we will iterate every step until the endpoint comes to our condition. And in this step, for example, if the sparsity is k, and we cannot make sure after k steps we get the desired solution. That's because in every step we cannot make sure this J0 is different with every single item selected before. So we cannot make sure this J0 is unique. That means after k steps, we cannot make sure we get the result. And to solve these drawbacks, and one improved method called orthogonal matching pursuit is introduced. And the only difference is just here. So the initialization is exactly the same. And how to find in current step, how to find optimal items is also the same. It's just we find inner product and the next calculation. The only difference is, so how can we get the coefficients corresponding to our selected items? And so so-called orthogonal matching pursuit we will also do this initialization step and update all these steps, but only different is here. And update the coefficients. At the orthogonal matching pursuit, so the solution is like this. We will minimize this L2 norms value, and the Y is original signal, but A and X is kind of a little bit different with original A. It is just items we selected in current step. Do you have any? No. And XS is we just want to solve what kind of coefficients corresponding to the selected items. So as this function, so we similarly we will still make the derivative of this function, and the derivative is just like to that is it's the same, and the derivative is how can we find this xs? Xs will get the derivative, and when the derivative equals 0, we find the xs. And so in this equation, as is the items we selected. So, but what's this one? xs. Actually, it is just equals to our k. And that means equals 0. That means in orthogonal matching pursuit method, the inner product of selected, in key step selected items, and the residue in key step, the inner inner product is 0. That means selecting items is orthogonal to our residue in current step. So this is why this method is called orthogonal as you pursue. And so by this way, we can make sure after k steps, we will find the solution corresponding to the k sparsity here. And this is the basic story of the sparse coding. But there are also other researches on how to find the dictionary, because our method is based on the dictionary is known, but there are other researches consider how to find the dictionary. And also, there are also other methods considered reusing the L1 norm to replace the L0 norm or something like that. But this is just a basic story of the sparse coding. And to this point, so actually I have one question. That means the sparse coding in a dictionary we have features. For example, in its original signal and its dictionary. At last, we find x1, x2, xk. This means when features we selected from these features selected k features, we use the features to reconstruct the original signal y. So it's kind of similar with one common used method in principal analysis. Principal components analysis, PCE method. So what's the difference between PCE method and the sparse coding? And so maybe all of you have to know the PCE method, but I want to spend some time to introduce the PCE and find so what's the difference between PCE and the sparse coding method. So in the PCE method, actually, we also have n features, and at last we want to find the most important k features from these n features. And sometimes k is smaller than n. And so I want to introduce steps how to calculate the PCE and then I will introduce y. So, for example, the eigenvector to denotes the key feature. The key feature is equals to the eigenvector y. So the first one, the steps of PCE, the first one is normalization. Actually, in previous sparse coding, we will also do this step. And the second step is very important, and we will calculate the n features covariance here. And the covariance, for example, we also have a A matrix. N is n features in the original data. After the combination, we will calculate the covariance matrix of original features. And step 3, when we get this matrix, we will calculate the eigenvector and eigenvalue corresponding to this matrix. And eigenvector. And
Can you clean over there first?
Huh?
Can you clean over there? Yes, just clean it.
oh,
Yeah, sorry.
we get eigenvector. The 4 steps we will run the eigenvector. And for example, if you want to find k, the principal feature, and we find the largest k eigenvector. This is what we want. That means the covariance matrix is k largest eigenvector we can use as the key feature, the desired key feature. So the first question about this is why we can use this covariance eigenvector to our key, using the key feature we want to find here. So suppose the key feature we use u as the item, as a new item, and original every feature will make a projection in the new item. And if we want to similarly list every diagonal elements on the variance of every feature, similarly we will find the variance of every new data. And the new data we can since our first step is normalization, so the mean value is 0 after some projection. It's the same. It's also 0. So we don't need these steps. And this is the variance of every feature, right? This time, and so this equals to and since it's just an inner product also equals transpose. This is the variance of the data. And we will find, so what's the value if we calculate the following, what's values like this. And since a zero product equals to this one, also equals to this one. So it's square, we can write like this. Right? So the variance is so like this. And since I has nothing to do with this u, so covariance can denote like this. And suppose this value is lambda. So lambda equals to U transpose and this value is over this value. So this variance can denote like this. Since U is the unit basis here, so if we left time on U, so we can denote like this. And since it's unit featured here, so this equals 1. And since lambda is just a real number, so U lambda equals to lambda U and equals to U. This one, right? So that means for this matrix, and we can find a real number can denote like this. So in linear algebra, so actually this is for this matrix, this is an eigenvalue, and this U is the eigenvector we want. So just look back this one, and actually this one is covariance matrix. For every item, we calculate this one inner product. So that means this is covariance matrix. So that is why in the second step we calculate the covariance, and in the third step we calculate the eigenvalue and eigenvector corresponding to this covariance. And this matrix eigenvector can be denoted as the new features we want. And in signal processing, actually we're using variance to denote the energy here. So actually this is new energy. The lambda is the new energy of the new features. And the next one I want to prove, as we know PCE method, when we find key features, actually every features are orthogonal. So I want to why it is orthogonal. And from this covariance matrix, actually it is kind of special since it is a symmetric matrix. And covariance A1, A2 equals to covariance A2, A1. So actually, this covariance matrix is a real symmetric matrix. And suppose we have a symmetric matrix C, and A1 and A2 are C's eigenvector. This is the symmetric. And eigenvector A1 and A2. So I want to prove for the symmetric matrix, actually the eigenvectors are orthogonal. So first of all, I want to prove this one. And so we know this is and since C is a symmetric matrix, then we got this is equals to A1 C. This is not product. That means for symmetric matrix C, and A1 A2 is eigenvector, we have this. This is correct. And suppose we have B1 and B2 denotes eigenvalue. So what B1, B1, B2? This will be equals to 1, since this is the eigenvalue of matrix C, so and since we have this property, this will be equals to A1 C and this A2 is A2's eigenvalue. So A1 and then will equals to A1. That means for symmetric matrix, for every eigenvector of this C, this one and this one is equals to this one. That means B1 is 0. And generally, this will we cannot make sure B1 is equals to B. So that means for any symmetric matrix, eigenvector is orthogonal. That means in PCE, so after decryption of the PCE method, I think just from mathematically we can find some difference. First of all, sparse coding we just selected from original dictionary. For example, from the 1,000 item, we selected original items for some several. But PCE is not. We have original items, but we transfer the original features into key features. The second one is the sparse coding actually selected feature. Maybe it's orthogonal, but generally it will be not orthogonal. In the PC actually the key features are orthogonal. So I think mathematically they're two different. But from the perspective of single or immediate processing, I think sparse method we just give a strict criteria of every, for example, the zero norm will be as small as possible, but there's no this property in the PC method. So that's all.